So for this video, we have 5 different gas laws we're going to learn. Each gas law deals with different variables, but first let's talk about the variables you will be seeing. The first one is P, or pressure. This variable determines how much pressure is being exerted on the container. Remember that the definition of pressure is how many times or how often a particle collides with the sides of the container. Pressure is commonly seen in atmospheres, torr, which is also equal to millimeters of mercury, and kilopascals. The next variable we're going to see is V. V is volume. Volume is how much space a gas takes up. Usually it takes up the space of its container, so the volume of your container will be the volume of your gas. This is commonly seen in liters, and that's really about it. The next variable we have is N. Let's do that in a different color. N. N is your number of moles, not grams, not particles, but your number of moles. And obviously the unit for that is going to be the mole. The next variable we're talking about is temperature. Temperature cannot be displayed on a degree scale because if we have negatives, then it wouldn't make sense. So temperature is always, no matter what, in Kelvin. The final thing we need to talk about is the ideal gas constant. This is just a constant to balance out basically all the units and cancel them out. So you'll see it in different pressures. So make sure when you're using your formula sheet for the ideal gas constant, you pay attention to the pressure unit. For example, it's 0.08206 liters times atmospheres over mole Kelvin. But if you're replacing atmospheres with kilopascals, it's something else. The first law we're going to be talking about is our only example of inverse or indirect variation. This law is called Boyles Law, and the equation for it is P1 V1 equals P2 V2. So this is indirect variation because you have basically a constant is going to equal xy, or 1 over x equals y. Those are both examples of indirect variation. So let's try a practice problem. Say our P1 is 2. Our P2 is going to be 4, and these are both in atmospheres. Finally, our volume is going to be 8 liters. So if we're trying to find our V1, we take our P2 times our V2, which is 4 atm, times 8 liters, and we get 32 atm times liters. I know the unit doesn't make sense, but keep this in mind. Now we have 32 atm liters equals 2 atm times our volume 1, which is what we're trying to find. So we divide by 2, and we get that our volume 1 equals 16 liters. And remember, atm will cancel out because this is also a pressure unit. The next law we're going to learn about is GaloSax Law. This is one of our 3 or 4 examples of direct variation. This law deals with pressure and temperature. So it's pressure 1 over pressure 2 equals temperature 1 over temperature 2. You'll notice that unlike Boyles' law, the variables are dividing by each other, not multiplying. This can also be expressed as pressure 1 times temperature 2 equals pressure 2 times temperature 1. So unlike the last law we faced, you have 1 times 2 and 2 times 1 rather than the variables from the same time being on the same side. So let's try a practice problem with this direct variation. If our pressure is given as 8 atm and our temperature is given as 52 Kelvin and our second temperature is given as 26 Kelvin, we need to find our pressure 2. Alright, so what we do is let's multiply our 8 atm times our 52 Kelvin, and we see that'll get us our pressure 2 times our 26 Kelvin. Notice that my units are in Kelvin here, and if they were in Celsius or Fahrenheit, I would need to convert them to Kelvin. So we're going to divide by the 26 Kelvin. That'll cancel out with that, including the units, and make it 2. So we have 8 atm times 2 equals our pressure 2. Our pressure 2 is going to equal 16 atm. Charles' law is another example of direct variation, so I won't be doing a practice problem for this one unless you guys comment below, and I will do a video with gas law practice problems. But all the direct variation problems are set up in the same way. So Charles' law relates volume and temperature. T1 over T2 equals V1 over V2. Just like with GaloSax Law, we can rearrange it to make T1 V2 equals T2 V1. And once again, temperature always in Kelvin. Don't forget to convert to Kelvin because Kelvin is not on a degree scale, so it can't be negative. Volume will most likely always be in liters. Alright, for this practice problem, we are given several variables. Our pressure is 3.0 atmospheres. Our volume is 27.0 liters. We are given the ideal gas constant as it'll be on all of your formula sheets, and we're given the temperature. The first thing I notice is that this temperature is in Celsius, and we need to convert it to Kelvin by adding 273. So when we add 273, we get it's 298 Kelvin. Now we're ready to set up our problem. PV equals nRT, so we can manipulate that to say that N equals PV over RT. So let's plug in our values. Pressure is going to be 3.0 atmospheres. Volume is going to be 27.0 liters. Ideal gas constant is going to be 0.08206 liters times atmospheres over mole times Kelvin. Notice that because the liters and atmospheres are on the top of the ideal gas constant, and they're on the top of our main fraction, they will cancel out. The next thing we need to put, if I can make some space here, is our temperature, which is 298 Kelvin. And that Kelvin will cancel out over there. So when we calculate this, we get 3.31 moles. However, the question is asking us what the mass of the gas is if it's pure hydrogen. Remember that hydrogen is H2 and its molar mass is going to be 2.016 grams per mole. So when we multiply that out, we get that we have 6.68 grams of hydrogen. The final law we're going to learn about is Graham's law of effusion. Graham's law of effusion predicts the rates when you compare multiple gases and how fast they exit a container. Remember that effusion is different from diffusion. Effusion is exiting from a container in between molecules. Diffusion is spreading out in a certain area. So, our law here is that the rate of the second gas divided by the rate of the first gas is equal to the square root of the molar mass of the first gas over the molar mass of the second. Now that's a lot of jumble, so let's just do a practice problem. We're trying to figure out how much faster hydrogen escapes than oxygen. We know that hydrogen will escape faster because it is a lighter gas and it has smaller particles, so it's easier for the hydrogen particles to get through. So, first thing we have to do is find our molar masses. Our molar mass of our first gas, which is going to be oxygen, since we want oxygen on the bottom, is going to be 32.00 grams. Our molar mass for our second gas, which is hydrogen, because we want it to be on the top here since it's faster, is going to be 2.016 grams. When we divide that, we get about 15.87, and the square root of that is going to be 3.98. Therefore, hydrogen effuses 3.98 times as fast.